Is that chapter 9 in the book?
It is chapter 9. I don't know why when I do white screen it stops on it and freezes up. Try to share again, maybe. Now I know why. All right. So the first section is talking about the quality, radiographic quality. So when we are evaluating our x-ray, the first thing we look for is what can we see, and that's kind of the quality, what we can see. And we have in the book, we'll look at it in a little bit too, there's like a little triangle that shows image quality, the visibility, what we can see or what's recorded. So we're gonna check it out, see if we can see all the anatomical structures and how accurate they're being recorded on the x-ray, and that's gonna determine our overall quality of the image. So on this, we have a visibility side on one side of the triangle, or the V upside down, and one side is sharpness. So visibility is controlled by, or we can, showing up, what we can see is by the KVP and math that we set. The sharpness is considered what we say geometric properties, and there's resolution and distortion. So we're gonna look in depth on those, all 4 of these areas in a little bit more detail in the chapter. So when we're saying visibility, what we can visibly see, we're going to evaluate it by the brightness and the contrast. How bright is it, and our scale of contrast that we're seeing. So we need to have optimal brightness, and the old term for that is density, so some texts may still say it. We're phasing out of that now. Digital's been around for a while, so now it's the brightness that we see on the monitor. So it's a lot easier to explain as brightness. It's much better for you guys to understand. And then contrast, that's the shades of gray that we see, so we can see different body parts so that we can visualize the anatomy and the area of interest. This is not on the PowerPoint that I posted. This is something that I added just now, just because we're going to start talking in these terms going forward in the future. The book doesn't say this yet. It hasn't been changed. The ASRT and them are looking to edit the test one more time. A few years ago, they edited it and took off some stuff that had to do with film. Now we're moving into more general stuff for just digital. So this is a term you're going to hear moving forward for what the receptor receives. It receives a signal. That's how it turns that, depending on what the signal is, into a shade of gray for us. So we're going to call it a signal on the detector when we talk about it. And that signal is going to give us a value of how much of the color and how bright it's going to be, the shade of gray on our image. So digital, we'll talk about this brightness and contrast in relation to the signal that the detector receives. Don't have to worry about it for our test this week. Contrast is, this is a definition, and this gets people all the time because it has brightness in it. So contrast definition is the degree of difference between the adjacent brightnesses. So if everything was the same, we wouldn't see any shades. So how much brighter or less bright the areas beside each other are is how we can see the scale of contrast. So the adjacent side-by-side brightness that we see, that's our contrast. On the overall scale of contrast, we have 2 types. Long scale, lots of shades, is low contrast. Short scale, big difference between them, not a lot of shades, is not as many, is considered high contrast. So long and low, short and high. For some reason, short scale people try to put low contrast with it. Long scale is lower contrast because you can see not a lot of difference between them. High contrast on shorter scale. We're going to keep talking about this for like the next week or 2. This is a book that somebody x-rayed. It's in, this picture is from your textbook. So this has a same atomic makeup. The book is solid with paper and whatever it's covered with, and they x-rayed it, and you don't see a lot of differences in it. So we're not seeing any kind of shades of gray, really. It's all almost the same. Lack of contrast appears homogeneous, or all the same color, all the same shades, pretty much. So we don't want that in our x-ray. We want to see differences in the brightness levels so we can see the different shades of gray. Here they took that same book and put some objects on it. They took a clavicle bone and some kind of material. It could be this screen mesh that we have encased in an acrylic, that circle shape. And then I'm not sure what this little rectangular shape thing is, maybe a stack of Post-it notes or something. But now we see differences. We see shadows, we see brightness, we see grays. So we can see the different shades of gray and the different contrast, different brightness levels overall. So radiographic contrast is how we can see visible items in our radiograph, the structural lines that make up it to record and make our image. So in this one, you can see all those little grid-like lines. It's like a piece of screen. And then it's different atomic makeup as the stripes are going across it. So over here, we're not seeing the lines anymore because of the thickness of it or the density levels in it. They absorbed it, so we're not seeing the makeup of the cross section, the little zigzaggedy crosshatch pattern. It's because it was attenuated. It was a little bit thicker, so over here, it showed up. And then the same thing off the book, the bone that's not on top of the book, more x-rays went through, so it has more black here, and then where it's over the book, it helped it to absorb some of the photons, so more got absorbed, so it's a brighter white. So an interesting thing that happened there with that bone. These little bright white things are metal in the clavicle that was from somebody's skeleton phantom to hold it on and connect it to the shoulder girdle and things like that. But so everything absorbs differently or attenuates the beam differently. Here's an example of a higher contrast image in relation to the abdomen. So in the chest, we have bone, fat, and air, lots of different atomic makeup. So we're gonna see a high level of difference between this brightness and dark areas. So this is higher contrast than what we're gonna see in the next picture. On an abdomen, everything's kind of the same. Muscle, water, and fat are almost the same atomic makeup. So we're gonna see not a lot of differences here in the abdomen organs. They're almost close to the same shades. Now, of course, we still have air and we still have bone, which is gonna absorb some, but this is a lower contrast than our chest x-ray, where it's more different, shorter scale. If we measured every single color on here, we might come up with 40 different shades. But if we looked at this one, we have a shade here, a shade here, a different shade here, a different shade here, a different shade, a lot more different shades of gray. And then right in here and right over in here, not a lot of difference between them. We can't really see a big contrast difference between the organs.
Point out where the air is? I just want to see.
Yeah, this black blob is air.
Okay.
This black bubble, and then down here we have a big black bubble. Right here, all these little black, like even this little squiggly, and this squiggly black here.
Okay.
Yep.
Thank you.
You're welcome.
What? That's like that squiggly line. Like, how would that be air? Like, is that good or?
In the intestines, you have air going through your body, so it's normal to see air patterns throughout the bowel. The small and large intestines both hold air, and it eventually gets escaped out of us in gas, and sometimes it makes its way up to the stomach and we burp, or sometimes it comes out through the rectum. It just depends. It eventually escapes, because if it doesn't, then our intestines would explode. So if we have a blockage or something. We also have over here on the side of this patient, the black area. That's not in them, that's just air on the outside on the table, on where the x-rays hit through onto the IR. Their body doesn't go all the way over here. So all this dark black around it is also just natural where the x-rays penetrated through and didn't interact with anything. Ooh, I don't know why I did that. Same thing on this one, all up in here, all this black and all the black around the sides, just where the x-rays went through and hit the IR. No body tissue was in the way. Right about here, this light shadowy of gray is where their skin stopped. You can kind of see it all the way up to their armpit area.
Is that a posterior view?
So this is normally a chest x-rays taken as a PA projection, a posterior to anterior projection. In honesty, there's no way to know if this was taken AP or PA because they should essentially look the same. The heart might be slightly magnified a little bit, but we generally accept that when we see an x-ray like this, a chest x-ray, that it's done PA because that's how we prefer our chest to be done. But good question. And then the belly picture, the abdomen, we usually lay them on their back supine. So this one is normally an AP projection. And abdomen is a little different. If it was PA, the pelvis would look weird because of the hip bones, the way they sit in the body. But we'll talk about that more in abdomen class. So two types of contrast, higher contrast, lower contrast.
Can I ask you something about that? I noticed both of these. Are we just talking about the pictures, or is bone, fat, and air is going to be a higher contrast? I know bone is, but I noticed you got fat on both of them.
Yeah, so the difference, good question. Each radiograph, it's going to be dependent on what's made up in it. So I could have two chest x-rays in theory. One would be a higher contrast picture than the other. It depends on the shades of gray that show up in it. These are just kind of two examples of the body where in the lungs, being most of our chest, it gives us a more higher contrast because they're such a dark area as compared to the muscle of the heart and the bone in the ribs, where in the belly, we don't have that. We don't have that super high attenuation change happening. So the organs are more similar. So this is considered a lower contrast area of the body, and this is a higher contrast, but it's not always that. So if that's what you're asking about bone, fat, and air, no, because I could have just a hand x-ray. It only has bone and soft tissue. We don't really have all that other stuff going on. That's way higher contrast than the chest x-ray. So we usually have to say either one thing, we're changing our KBP to change the scale of contrast, or we're comparing two x-rays with each other and saying one's higher or lower contrast than the other.
Okay. All right, thank you.
You're welcome. So in that, we can change our scale of contrast when we have a more penetrating beam because it's going to go through more transmission and it's going to have more areas of dark. So that's when we get into adjusting our factors for changing our scale of contrast and making more things show up or not, depending on what we're wanting to do. So KBP and contrast have an inverse relationship. If one goes up, the other goes down, and vice versa. So if we increase our KBP, we are decreasing our contrast. Because the more KBP we have, the more transmission we're going to have, and overall, that's going to give us more different energy levels in our beam. So more shades of gray are going to end up happening on our picture. If we lower our KVP, we're going to have more photoelectric effect happening. So more absorption, so more black and white. That's a hard one to get to. And you know from the beginning of week 1, KVP is that potential difference that gives our x-rays their energy level. So our photons get their energy from that potential difference that we apply to the tube to how fast the electrons are going to slam into it. The more energy, the more transmission. Now, we also have to think about our thickness of our part, the anatomic number of our part, and other things when we're picking the energy we want. So our contrast comes from those different degree of densities in the patient and how they are going to absorb or let the x-rays come through. So we have to kind of go by a range of what we have for each body part and pick the best number of kVp that we want for that patient, depending on their shape, size, thickness, and if we know what's going on with them, if they have something pathology-wise going on. Sometimes we don't know, and then we look at the x-ray and we decide we need to do a retake to get a better picture. Kilovoltage affects the x-ray beam quality. That's our primary thing that we look at with the kVp, but it also affects the quantity, because as we increase kVp, we're making our beam more penetrating, so more photons are going to go through the part. So kVp does both. Primary controlling factor is quality, though, the penetration. So the x-ray beam penetration is going to give us how much is going to be absorbed in the tissue. Increasing kVp increases penetration, decreases absorption. I think we're all good with that. Decreasing kVp decreases the penetration, increases the absorption. So altering our kVp is going to change the absorption and transmission in the part. So here's two pictures of a chest. Top one has higher energy photons going through. So you can see that we have a different scale of contrast, shades of gray in that than the bottom picture. The bottom picture is lower energy, so more absorption. So overall, it's a more black and white image. It kind of pops a little bit better. So the top picture is a decreased contrast or a longer scale. The bottom picture is a higher contrast or an increase in contrast, more black and white. Does everybody see that?
Yes.
Thank you.
Okay, so the top picture has a lower contrast. It's brighter. So therefore, it has, oh, let me think this through. It has, okay, so it's brighter. So it has a lower kVp?
No, don't say brighter.
Okay.
They both, to me, overall the brightness is the same. The difference is the shades of gray that you see with your eyes. So the top one is more grayed out, more similar where the ribs are, especially in this area here. When we look at this one, see how they pop more? It's just black and white. Here it's kind of mixed together, the grays. You can still see the ribs and everything. But even across here through the heart area, you can see a rib, a black area, a lighter area here, then the heart's really white. But then here, it's like super black and white change and transition.
So the second picture has a higher contrast, so then it has a lower kVp.
Correct.
Okay, thank you.
More absorption happened in here.
The only thing for me is it's weird, like if you increase kVp, you increase the transmission, so I would figure that you would see more black in a high kVp because it's more hitting IR.
But with higher kVp, you're changing the energy of all of your beam. So they all shift to a little bit to the right side. So those ones that were going to be absorbed are still going to be absorbed. We just have more of them.
Okay.
Are getting the shades absorption is going to be different.
Okay, so I want to understand. So I'm thinking, I want to make sure I'm correct.
Mm-hmm.
If you lower the kVp, it's going to take longer to go through. So that means it's going to go through slower, but you're going to absorb more of it versus if you increase the kVp, it's just going to shoot straight through it.
Okay, so one thing I don't want you to think about speed. I know you're thinking about it as penetration.
Yeah.
They all go through at the same speed, the speed of light.
Okay.
But they are more energy, so they can go through more with a higher kVp, yes. And the lower KVP, more likely that they're going to get absorbed in the tissue. So just think of it as that.
Okay.
So higher KVP, more energy.
Correct. And with that, more energy, that's where Michael was kind of going. We shift all of our photons energy over a little bit. So even though we're making them more penetrating, we're also increasing the ones that are going to be absorbed to the number of those. And that's going to give us a more number of shades of gray, because those are also going to be absorbed differently in the body. The same amount as before went up all the way across the scale, not just transmission. So that's why it's not darker as far as we're saying contrast scale. Now, what Michael is talking about is a whole nother concept, and that is the exposure to the IR. Transmission to the IR was more with the higher KVP always, but the shades of gray increased across the board. So higher KVP is more shades of gray, so a decrease in contrast, lower KVP, more absorption, less different shades, because we're going to have more black and white.
And higher transmission, right?
With higher KVP, yes. Higher transmission, yep. So transmission has to do with exposure to the IR, how many photons are going to hit the IR. But the contrast is really more or less talking about how many of each shade is going to hit the IR in an area. So things that can change or influence our contrast, and we talked about this the other day, some of these. We're going to get into all of these things as a bullet point today, but with regards to this OID and grids, that's a whole nother chapter. We're going to look into that a lot deeper, but this is just giving you the bullets of everything that could change our contrast. So KVP is considered the primary controlling factor for contrast. We use KVP, the penetration, the energy of our beam, to tell us the scale of contrast we want for our image. Other things can affect contrast, and this is where it gets really tricky with those charts and stuff in the book. The distance of our object to the image receptor. So OID is the object to the IR, how far away it is. We use a thing called air gap technique to help reduce scatter, and that's why we're going to talk about that in another chapter. But we do sometimes have an object not sitting right on the IR. So we say that's OID. So one example, and it's easy to think about, is our C-spine. We have shoulders in the way. We cannot put our C-spine directly on the IR. So we're going to have a gap, a few inches. So in that gap, X-ray photons are going to diverge before they hit the IR. Some of those photons are not going to make it to the IR. So less shades of gray hitting the IR. So it's a decrease in contrast.
What did OID stand for again?
Object to image receptor distance. So how close our object is to the image receptor. So in that C-spine example, our neck cannot ever touch the IR. We're always going to have a gap on a side view, lateral, sorry. If I'm laying down, it's flat to the IR pretty much. Even then, in the Bucky, the IR is in the Bucky a few inches back. Everything has a little bit of OID. Nothing's ever directly touching the IR. In our skin, we have some tissue on our fingers. The bones aren't, the hand aren't touching. In our chest, our heart is not touching. So we have a little bit of object to image receptor distance with the heart. So everything's going to have a little gap in the beam diverging through before it gets to the IR. So the more we bring away our part from the image receptor, we're increasing the object to image receptor distance. So OID makes the scale of contrast change. If we are increasing contrast, actually, because we're taking away photons from hitting the IR. So air gap technique helps to improve our contrast. Grids, I didn't want to talk about grids yet. Just know grids also remove photons, and so that increases contrast. We'll talk about those in a whole nother chapter. You guys
Doesn't that helps improve the contrast? So that means it helps it by making more black and white.
correct. Good. Improving contrast means a shorter scale, more black and white. Going up, contrast goes up, higher contrast, shorter scale. Beam restriction. What we're talking about with beam restriction is how much area are we x-raying. So you guys have been messing with the collimator and opening up to a 14x17 or a 10x12 IR size. But what if we were just doing the C-spine and we have a 10x12 opened up this big around the neck? Do we need all this air spot here on the front picture? No, we can come in. We can restrict the beam to just the area that we want. So the less area we have, the higher contrast we are gonna have, because we're gonna reduce scatter. And again, that's a whole nother section in the book, another chapter we're gonna talk about. But beam restriction, the more you can restrict the beam with those lead shutters inside the collimator, the better your contrast is gonna be, improving contrast, higher contrast. We can't really do much about the part thickness, but this is why mammograms get the boobs compressed. The tissue gets compressed as much as it can to decrease the thickness of the part so we can improve contrast on the mammogram image. We don't really do that on anything else. Sometimes you could do an abdomen like that and put them on their belly to smush the belly to decrease the thickness of it, but not normally. But if we can decrease the thickness of the part, less tissue to go through, we're gonna improve the contrast. Filtration, we talked about removing some of those photons from the beam. So that of course is going to be a different, taking away some of those X-ray photons, reducing the beam from being able to produce another shade. So the more filtration, you're gonna improve contrast. And then we have two types of pathologies, additive and destructive. Additive pathologies are like we were talking about yesterday, fluid in the lungs. That adds to it. Destructive takes away, like osteoporosis, taking away the bone. So if you have an additive pathology, you're adding to the tissue, you're going to be decreasing the contrast. Destructive is going to increase the contrast. There's not a lot there, more black and white. So all these things have an effect on contrast. Controller is KBP. That's what we use to adjust for all these different things when we do these things in our everyday. You don't even think about it really, you just do it. So one day that'll be you guys. But for now, we are going to just have these as bullets, things that affect contrast. For the test, number one thing you need to know is KVP is the controlling factor for contrast. If you increase KVP, what do you do to contrast?
Increase.
Increased contrast means what? Shorter scale or longer scale?
Shorter.
You said if you increase the KVP,
Or
you
longer.
decrease contrast.
Or
Yeah,
You increase the
Short
KVP,
scale.
you're decreasing the contrast. They're inversely related.
decrease contrast. Good, inversely related.
Woo, scared me.
Yeah. So if you decrease KVP, you're making it more of a shorter scale, which that means higher contrast or an increase in contrast. Those words get people.
Now, I know in one of those slides, I think it was the second one, you had like visibility and like properties, and it's KVP and mass. So where does the mass, where does that come in to play as far? Is that, what's that?
We'll get there in a minute.
Okay.
We're going to get to the mass section. We're still on the contrast section. So I went over all this as I went through those bullets, guys. I'm not going to make you go into this too much right now because we have a whole chapter on OID with grids and OID. So just know object image receptor changes the exposure to IR.
So really learn.
Yeah, I mean, I'm not even going to have this on the test yet because we have a whole chapter where we talk about OID and how it affects and changes contrast. It's just in here because it has an effect on it as the bullets. And this kind of draws it out and shows you it. What I was talking about, object to image receptor, and how as the objects have x-rays go through them, the beam's still divergent after that. So it's a possibility that it's going to not make it to the IR. So it reduces the exposure. And it also changes the scatter that's happening. And so some of the beam's getting scattered too. We have grids in the Bucky, the wall Bucky and the table Bucky. And again, grids is a whole nother chapter we're going to go over. So they affect how much photons are going to make it to the IR. There's lead in these grids and they absorb some of our photons. We're hoping they absorb our scatter so we don't have scatter fogging up our image, but that's another chapter. We're not testing on that this week. Just know that grids help increase our contrast. Collimation, the more we can collimate with our lead shutters to the part that we're x-raying, the better it is. That reduces scatter and higher contrast, improves the contrast. Again, collimation is a whole nother section that we're going to talk about. And I'm going to make you guys have a little paper collimator and show you the shades of gray that it's going to change when you collimate. So again, just know collimation can affect contrast, but you have to know all the stuff that's on the slide right now, because we're going to go into that in next week's chapter on collimation. You know, filtration takes out some of the photons. So if you add filtration, you are making the contrast shorter scale contrast or improving contrast. Pathologies, additive and destructive. Additive pathology is something that is going to absorb. So I don't like how that's worded. Absorbing is going to take away photons. So a shorter scale contrast, yes. Destructive takes away out more scatter. Additive's going to have more scatter. I don't like how that's worded at all. Additive pathology. Let me fix that real quick. Oh, I don't know where that is. Re-upload this one. That's not true. Oh, I didn't notice that before. So additive pathology is like fluid in the lungs. It's going to cause more area to be irradiated, some more scatter, more shades, longer scale, contrast, destructive, osteoporosis. That takes away bone. So this is going to be easier to absorb. More black and white, short scale. So the front of the book, it used to be, now it's the back of the book, your little pathology chart that tells you additive and destructive pathologies. You don't need to know all those additive and destructive pathologies now, but in the pathology section of the program or each positioning class will go over those main ones that are additive and destructive. For this test coming up, I want you to know that additive pathology adds to the atomic makeup of whatever wherever it's at. So a tumor could be an additive pathology. A tumor could also be a destructive if it's eating away at the bone. So I just want you to know additive adds, if it's considered an additive pathology, adds to the atomic number. Destructive takes away, destroys it. So it's a lower atomic number, easier to penetrate.
So like if you're adding something like you said, the fluid, if you're adding to the picture to be seen, or if it's destructive, it's like degenerative disease or whatever, or discs, it takes it away.
Yep. So
Can you
that's
repeat that one more time?
So additive pathologies add to the atomic makeup of it, and destructive is like degenerative diseases that take away or destroy. So if we're adding to it, just say you're adding to the Z number. If you're destructive, you're taking away from the Z number of the part of whatever its pathology is messing with. So we have most of our pathologies that are additive are going to be fluid related in the body.
And you said additive will be
higher Z
easy
number.
to go through or not?
Not easier, more absorbed.
Okay.
Yeah.
It'll be white.
Yep, white.
So additive, white, destructive.
Increases contrast. Additive.
Yeah. So a longer scale with additive pathologies because it's going to be more grayscale. Destructive is going to be more black and white, short scale. Because there's not really a lot there. It's going to either go through it and show up as black. So I'm trying to think of an easy one that shows up. Destructive, like in the lungs, would be a pneumothorax. Air leaked out of the lung is going to be black. So that's going to be just an easy to see black and white on the x-ray. But fluid in the lung, like pneumonia or pleural effusion, is going to be a fluid filled area at the bottom of the lung, and it's going to be a grayed out area. So kind of all longer scale for fluid, and destructive when the air would be easier to see, shorter scale. So if we say something is high contrast, I think somebody just got that a minute ago. High contrast is more black and white. Lower KVP settings, so we think bones, the hand. This is considered short scale. High contrast also is considered increased contrast. The maximum difference is easy to see between the brightness on the screen or the darkened lights. And this is a new term called latitude. Narrow latitude just means not a lot of changes between it. A wide latitude, lots of shades on the grayscale that we can look at. We also say dynamic range, lower dynamic range or higher dynamic range on the range of densities or grayscales that we can see. But most of the time you're going to hear increased contrast and decreased contrast. That gets people's minds messed up. An increase
The other terms?
Huh?
Like recognize the other terms for our test?
You want to know probably all of them, but the main ones that'll be on the test will be an increase in contrast, or short scale, long scale, or high contrast, those three. That's what I've seen most tests ask. So if you want to make an improvement in contrast, that's increasing contrast. So that means you need to lower your KVP for a more black and white image. Higher contrast, lower KVP, more black and white image. Now the other side of that is the opposite, low contrast. That's going to be lots of shades of gray, long scale. We could also say a decrease in contrast or less contrast. They kind of look all close to the same shades on it, many shades of gray that you can see. In this, it's where we're looking at mostly soft tissue area in the abdomen where everything's made up of the same tissues. But I could take in the lab and do a hand where we hardly see anything because I use such a low KVP, we lose contrast. I could go super high on my KVP where it's all black, where we lose contrast, but that's a whole nother thing. So you have to be within a certain range. So that's why we have that dynamic range that we talk about, wide latitude or narrow latitude, meaning wide, lots of shades of gray, or narrow, not a lot of shades of gray. But most of the test questions, if you have any relating to contrast, will say low contrast or high contrast. Low contrast means higher KVPs are used when you want to say you're seeing lower contrast. High contrast, we want more photoelectric effect happening, lower KVP, so we see more black and white. As you go up in KVP, you're changing the energy of your beam, so we have more different energies to interact differently with the tissue, so we get more shades of gray. That's how I always try to say higher KVP.
And the high contrast is more associated with photoelectric
Yep,
effects.
yeah, photoelectric, because in those you're either going to have them absorbed or sent through, transmitted, where you see the difference in the black and white better. Less contrast for some reason, or decrease in contrast, gets people. A decrease in contrast means we are going down in contrast, not as easy to see the differences. So lots of grays that kind of look similar. A decrease in contrast is long scale. So these I would write on a note card together. And then on the other side, have that say long scale or low contrast, whichever word you want to start with. Here's brightness, Kevin. So the brightness that we see on the screen, that's how much exposure the IR got. I can use the same KVP, but change my mass. That's going to give me a different number of photons to come through. So
Is number 2 a low contrast then?
yes, very short scale, just black and white. That's all we see. But number 4 has more shades that we see. Number 8 has a lot more shades. I guess they're saying 2, 16, and 256. This is what we can visibly see. Now, I could use this example and say we used 60 kVp. Probably really didn't, but if all 3 of these were done at 60 kVp, the brightness that we're seeing is by the computer, what they adjusted. So just like you can do on your TV screen, you can adjust it up and down, or your phone on a picture. It's losing or saturation, you could say. That's why it looks so crazy on number 2. We've lost all of the shades. It's just either black or white.
Yeah, there was, when I got the x-ray on my knee, when he showed me on the computer, like he just like right clicked his mouse, and if he moved it up, like it'd get like brighter, and if he moved it down, it got lower, so I could see it a little better. I don't know if that's kind of
That's
what
exactly it.
Right.
So we're going to go into that in a whole nother class too. On digital, you can do what we call window level, window width. One changes contrast, one changes the brightness of it. So you can change your scale of contrast, your shades of gray. You can change how bright we see it for the brightness of the image. So brightness of the image is to do with the exposure. How many photons we got through. So if we don't have enough photons, we're going to have a low mass, not a lot of photons. If we had a certain amount absorbed, it's going to be a really bright image. But if we have too much mass, too many photons made it through, it's going to be a really dark image, less bright. So that's what our mass does, is our brightness.
Okay, so I'm going to try to understand this. So X-ray 1, right?
Uh-huh.
Is the contrast too high on that?
Too short. Short scale. Too low. Too high, yes. Too high contrast, short scale.
Yeah, so it has too much black and white.
Yeah.
And that's what high contrast is.
Yes.
So that's no bueno. So number 4, okay, I get it.
Yeah. But if we're just talking about brightness, they all look about the same to me as far as how bright it is. I mean,
But the contrast of it.
so here's that abdomen again. we can say the black spot is a lower bright area, low brightness. Up here where it's white is a higher brightness, more bright, white. That's a weird thing to say, high brightness, low brightness. So the old term was density. This should say exposure. Fix this since I'm going to re-upload this. Exposure is how many photons made it to the IR. That's going to tell us how bright our X-ray is. So how much exposure it got is going to give us the overall blackening of the image. I guess I did say in digital we call it exposure. We used to teach both density and exposure, but they took density off the registry now. The more exposed an area is on the image, the more black it will be. When we see it on a computer screen, when we view our images on the monitor, that is called brightness, how bright it is. So it's the amount of light or luminescence coming off the display. So how much it hit the IR, that's the exposure. That's going to tell us when we process it how bright it is. Super, super crazy that we have to have two terms, but when we view it, we're saying the brightness of it. Exposure is how many photons hit an area, how dark it's going to be. Now, the difference between those exposures or brightnesses is the scale of contrast or the shades of gray that we get. So they kind of go together a little bit, they overlap. But we could have the same penetration with different number of photons that we change, and that's going to give us more bright or less bright, if that makes sense. In the same area, the penetration is going to be the same, but because we changed the number of photons, we got more that made it through, so it's brighter. And that's going to be something we'll experiment with in the lab. Not tomorrow, maybe, but we might try it. So here's two knee x-rays. So like you were just talking about your knee. They could do this and manipulate it on the monitor after you take the picture now. So that's one good thing about digital. With film, we would have had to do another exposure with a different amount of KVP and mass changing. So here's a really bright one and here's a really dark one. So this one is not exposed as much as this one. This one had more exposure. So this one on the right has more mass. Now, could we have done the other thing we could do is change our KVP, which changes our penetration, so more photons hit through. But mass is what we use to control our exposure. Because if we double our mass, we're doubling the number of photons that made it through. And that way, we're not changing our scale of contrast because we're not changing our penetration. So mass is our primary controlling factor for exposure. Knowing in our heads that KVP does change the number of photons making it through, that it has an effect on exposure. MA and time, that's our two things that equal mass. MA times time or seconds. Mass and exposure go together. If you increase mass, you increase exposure, directly proportional. Now, I showed a lot of you, I think almost everybody in the lab, if you change the time and MA, you get a certain mass. I think I used 5 mass the other day. 5 mass can be achieved by doing 2 different sets of time and MA settings. This is called the law of reciprocity, that you can have a variety of MA and time that can equal the same mass. So if I just use 1 second at 100 MA, 100 times 1 is 100 mass. But I could do 50 MA at 2 seconds. 50 times 2 is 100 mass. So there's still the same amount of photons being boiled off, just a different time and MA setting. That's just what the law of reciprocity is, that you can have multiple combinations to give us the same amount of mass. So if we say insufficient or excessive exposure, that's either overexposed or underexposed. We didn't get enough photons through or we got too many through. We are using mass to adjust and fix that. So if you did a chest x-ray and it was super, super light, you could see that the penetration was there, photons made it through, but we feel like it was just a little too bright, we could increase our mass to increase our exposure. On the other hand, if our knee x-ray was too dark, too many photons made it through, we could half our mass and cut the exposure in half. So we use mass as an easy way to control the darkness of our image or the brightness of our image, of how much exposure we had. Everybody good so far? So here's a big change in a hip x-ray. Ooh, super dark, can't really see the hip joint. There's the head of the femur, the neck, the trochanter over here. And this one, woo, too light, too bright. You can see kind of the trochanter, but really don't see anything in the head or the hip area. So both of these are bad. One's too light, one's too dark. We need to be Goldilocks and Three Bears and find just right. So this is kind of a rule. To see a change, a visible change, we have to change our mass by 30%. But most of the time, our minimum is doubling or halving the mass, so we can see a big change in our exposure. So if you go with letter A, say we use 5 mass for that, I would want to go up at least to 10 mass to see a doubling of exposure. Really and truly, they might have needed to go to 15 or 20 mass. But letter B, say they used 40 mass, super dark, cut it in half to 20 mass and try again, see if we get a good exposure. So somebody is going to have this for their experiment in the lab. Going to have you guys do just changing your mass on an exposure. We might actually do it on the hip and pelvis group.
So repeat the rule again.
Yeah, so the rule is to see a visible change, this last little comment here, that you have to do 30% just to see any change. But in general, we double it or half it so we can see a big change in the exposure.
So that last little part there, that's the rule of reciprocity?
Reciprocity just means that you can do different combinations of MA and time to get mass.
Okay.
So that's different.
Okay. So
This is how much change is needed. We can do 30%, but that's just a small little change in the exposure. Most of the time, you're going to see a tech either double the mass or half the mass to get more exposure or less exposure. Got a question? Let's see. Chat.
It's from me. It's not important. I just didn't want to forget it, so I sent it to you.
Okay. So KVP is our secondary thing. It's not our primary thing for exposure, but if you change your KVP, you're changing the penetration. It's not proportional direct because remember the 15% rule. If you increase by 15%, that does the same thing to our photons energy. It gets twice as many photons through. So it's the same thing as doubling the mass, we say. We're not changing our mass. It's effectively doing the same thing. But because of the change in contrast with KVP, we don't use it to control our exposure. We want to use mass to change our exposure. But you always have to remember that 15% rule. If you do increase KVP, you're effectively giving it more exposure. So sometimes if we do want to change our penetration, we will change our KVP, but we have to adjust our mass to make sure our exposure is maintained.
Is that always that way? So if we always increase it, do we have to keep that in mind to always like decrease the mass?
It depends on what you're trying to do. So not always. You will see techs use the 15% rule instead of changing their mass, but they're changing contrast and exposure with that. And I'm going to have another group do that with 15% changes in KVP and keeping mass the same and see what happens. So here's what they've done on this experiment. A was done at a certain KVP, then they upped it, and then they tried to maintain it, decreased it here, and then this one, their last one, they did the adjustments with mass too. This one's a picture from the book. But changing the kilovoltage has changed the exposure and the shades of gray that we see. I like letter D. You can see everything pretty good. Maybe a little burned out on the sides here. Letter A might be our best choice if you're going back and forth between B and D. This one's not enough. This one's too much. And that proper exposure is going to be your eyes, dependent on you and your radiologist, how they like to see their x-rays. Good thing is digital now, you can do what Michael was talking about and change it a little bit and adjust it, and it's okay. You don't have to do as many repeats like we used to do with film. So our primary factor for contrast, KVP, primary factor for exposure, mass. A lot of different things can affect the contrast, all those little bullets. With exposure, you really have a few things that can affect it and change it, like the KVP can, if we increase KVP, we're effectively doubling the mass, and then these other things that can change. Distance. You guys already know what SID is, the source to image receptor distance. That's how close our tube is or how far our tube is away from the image receptor. Our main two that we use are 40 inches and 72 inches. OID is object to image receptor distance, the object to the image receptor. So SID, we use the inverse square law. The intensity of radiation getting to the IR is going to be inversely proportional to a square of the distance. So if we go further away, increasing our SID, we are decreasing the intensity reaching the IR. If we come in closer, shorter SID, we are increasing the intensity of radiation reaching the IR. Another group is going to do this as a project for your exposures, keeping the same technique and doing one at 72, one at 40, and seeing how much more exposure you're going to get. Effectively almost 4 times more, but just for you guys knowing that SID changes exposure to the IR. Further away, less exposure. The photons are going to spread out more. Closer, more exposure. They're going to hit the IR. Everybody good on that one?
Can you repeat it one more time, please?
So if you're at 72 inches, we're going to have our beam diverge out. So not as many photons are going to hit the IR. If I come in to 40, same technical factor set, more photons are going to hit the IR. They're not going to have enough room to spread out. And it's the same thing as exposure to us when we're in fluoro and we step closer or further away. It's the inverse square law.
Thank you.
OID, that's the scatter and the radiation reaching the IR. The further away our object is, the more it's going to spread out. So less exposure to the IR when you increase your OID. So we're going to talk about that in detail in the OID section later. So don't worry about that for today. Underexposed just means it's bright. Not enough photons got to the IR. Underexposure, insufficient exposure. It's our image on the left. Overexposed means too dark, burned out the bone here. Can't really see the edges. Overexposure is excessive exposure. We use too many photons. Too dark. And that is the first part of the chapter about the visibility. Things that we can see on our x-ray are controlled by the KVP and the MAS, the contrast and the brightness. So that's our visibility properties, contrast and brightness.
Overexposed. Okay.
Okay, Michael.
Well, I was just gonna say overexposed is kind of like overcooking something. Like it gets darker, it gets burnt.
Yep. My mom likes them burnt. I don't. We actually had a student
Bones?
do that. Not bones, cookies.
Just kidding.
Oh, I was like, are we talking about x-rays here?
We had somebody cook the cookies and make them undercooked, overcooked, and just right for exposure. We used to do fun projects, guys, before COVID.
We can still do that. We can still make cookies.
Yeah, if someone makes cookies, we're not going to be upset.
We'll make cookies.
Before we go to the next part, can you just do like a quick recap of the mass and exposure and brightness?
Yep. So the two factors, that's what she was wanting me to repeat. that we see for visibility are contrast and brightness. Contrast is our shades of gray, long scale, short scale. Higher KVP, longer scale. Lower KVP, shorter scale. Brightness is exposure. How many photons expose the IR? We use mass to control that. Not enough exposure, underexposed, too low mass. Overexposed, burnt, dark, too much mass. Good. All right, let's look at the other side. Now, the other side I like, and this is our lab tomorrow, and we'll try to do some of these exposures too. This is the geometric side, and this comes into play with the sharpness of our image or distortion of our image. So two things, two sides to the geometric properties. How well can we see it? How sharp and crisp and clear is it? Or is it distorted in any way? So we have size and shape, two types of distortion we're going to look at. So spatial resolution is how sharp it is, how clear it is, and then size and shape distortion. Sharpness has a couple of different names, recorded detail or spatial resolution. So how sharp are the lines recorded on it? Spatial resolution is how we measure it. It's the smallest area that you can see on an image. And then distortion can be misrepresentation of the size or the shape of the part. So we want to have the best possible spatial resolution and the least possible distortion. It's not always achieved on every single radiograph, but we're going to look at the ways that you can hopefully get those two things to the best of your ability each time. So spatial resolution is kind of the definition is the ability to separate two things from each other visibly on a radiograph. Spatial resolution has to do with the objects, the anatomical body part that we're looking at, and it's better for areas that have high subject contrast. This gets people because subject contrast is talking about the person, their body, what they're made of. It doesn't have anything to do with long and short scale contrast. So it plays a role, but it's talking about the makeup, the anatomical makeup of the subject. So bone and soft tissue, breasts with calcifications, nodules in the lung that you would have to be able to pick up on an X-ray. This is a tool we use. It's the line pairs per millimeter tool. That is how we measure resolution. This is done by either a physicist that comes in or a person in the department that is in charge of checking out how well our resolution is, or the radiologist could probably try to do it. So we measure resolution with lines pairs per millimeter. How many lines can you see on the X-ray per millimeter? You just need to know this is the tool that we measure spatial resolution. You were going to go over in this in depth more in your next physics class. Line pairs per millimeter is how we measure spatial resolution. So if somebody's moving, you are going to have motion in the picture. The patient, the image receptor, or the tube could move. Any of those things is going to be a decrease in the recorded detail or the spatial resolution that we see. So if you think about a picture and you're taking a picture of somebody running home to first base when your kid's playing sports or something, or a football being thrown, or a baseball being thrown, or a car driving really fast, and it's moving, it's going to be blurry on the picture. Same thing happens in an X-ray. So this is bad resolution, this picture. The birds, looks like somebody was taking it from a car, and it has motion or blur. So this spatial resolution is the sharpness or distinction between the lines that make up your image. So You'll probably hear it called just resolution just because we like to shorten things. And we don't say spatial resolution all the time. We want to minimize the image unsharpness. Here's a special word, penumbra. Miss Steen loves to say penumbra. So you'll talk about that more in the next physics class, like I said, but penumbra is the unsharp outer edges of an object on a radiograph, or a blurriness of it. So looking at these two images, letter A has less penumbra than B. Image A has better resolution than B. B image is magnified. You can clearly see the lines in letter A, all little vessels, much better than letter B. And these are from your book, these pictures. So the spatial resolution is clearer on A.
So in penumbra, that's when it is sharper, like when it's clearer?
It's a word that means blurriness or
Okay.
It's just a definition for a new word for you guys.
So B is more penumbra than A.
It's more but penumbra, yes.
So the better an image looks, like quality-wise and good edges, the less the penumbra is affecting it.
Yes. So motion is one of the main reasons that we would have an unsharp image, and we have voluntary or involuntary motion. Voluntary is how we can best tell a patient, given good instructions, that's how we can control voluntary motion. Don't move, don't breathe, hold your breath. Using immobilization devices and using short exposure times can help with this voluntary motion, especially with kids. The shortest exposure time, the better, because they cannot hold still. We sometimes do a hand x-ray where they have to hold their hand at an angle, and that's kind of hard, especially if your hands shake. So we want to give them something like a sponge to hold it. When they're breathing, that's motion, so we tell them to hold their breath on most of our exposures. You'll get in such a habit, you'll be doing a hand where they don't really move, but you'll still say hold your breath. But what about involuntary motions? Can anybody think of what we have inside our body that moves that we can't tell them to stop moving?
Your heart.
Yeah.
The heart.
Yep, the heart, that's our main one. A chest x-ray, the heart's beating. We can't stop it. So we don't really control that involuntary motion. It's just we use that short exposure time and hope the heart beating isn't shaking their whole chest when we take the x-ray. We also have peristalsis in the abdomen. So here's some that have motion. It looks like we have a knee and we have an abdomen. The patient was breathing and everything kind of looks a little fuzzy and blurry. So both of these would have to be repeated because we've lost some recorded detail or resolution due to motion. So other things besides motion that could cause unsharpness, and these are the things that we're going to talk about and do some practice in the lab tomorrow to look at. So if we increase our SID, that's going to give us the best resolution or recorded detail. Decreasing the OID, so less OID, getting our object close to the image receptor. And here's the focal spot size. I kept telling you guys we'd get into this. The smallest focal spot size is going to give us the best recorded detail. So here's the info on focal spot size. It affects the sharpness or the spatial resolution because when we are bringing our filaments, boiling off those electrons, we want our beam to be tighter and closer together so it comes down more straight up and down. So the smaller focal spot size is going to give us a tighter beam, more condensed, closer together as it diverges. So that's going to give us a more true size and shape and resolution on our x-ray. So picking the small focal spot helps with resolution. Where do we pick this? How do we control focal spot size?
The angle of the, or no.
The filament.
The filament selection, and we pick that out on our control panel. So our one room, we have those different MAs. One says L and one says S. The small one is the ones that we say do not use. That's where we're picking our focal spot size selection. So we control it at the control panel. On the digital room, there's a button that you push for small and large focal spot size. So we'll look at that as you go into the room. Most of the time, it's a button or it's already programmed for small focal spot for parts that we want to use the small focal spot. But you can always change it and adjust it. But we do get to pick that, which filament we're going to use. So other things for spatial resolution or recorded detail, I think you'll probably hear spatial resolution mostly. And decreasing spatial resolution is magnification. So we think of magnifying something as good, but in X-ray, it's not good. It's an inverse relationship. The more we magnify something, the less resolution we're going to have. So we say, think about a flashlight. If you have a flashlight app on your phone or you have a flashlight in your house sometime today, and I have you try this, let me show you if I can get it to work. So if I put my flashlight on my hand closer and further away, the closer I am, the better the edges of the beam are, the circle looks better. The further away you get with it when you're doing it on a wall, the fuzzier it gets around the outside or penumbra happening. So the same thing happens when you magnify on X-ray with our part, and we're going to talk about how magnification happens. We call this magnification size distortion. So things that are going to affect our magnification or our size distortion are SID. If you increase your SID, you're going to decrease magnification. So interesting thing happens. The further away we are, because of the way the beam comes through the part and crosses through, it increases the resolution of recorded detail. So that's why we do the chest X-ray at 72 inches SID, because we want to decrease magnification of the part. Short SIDs increase magnification and decrease recorded detail. And this all has to do with the divergence of the beam through the part and what happens as it's passing through the patient. So your SID is pretty much controlled by the part we're doing. So we do a lot of things at 40 inches. We know it's going to have a little bit of magnification, but we specifically use 72 inches on a few things to help reduce the magnification. So a chest X-ray is one of them.
So the further away the source is, the less magnification?
Yes.
How come we don't do more X-rays at 72 then?
Well, there's another trade-off with technical factors that we'd have to increase.
I would figure the closer it is, the better it is.
You would think that, I know. Go leave it to X-ray to be backwards. So here's the picture in the book. And we're talking about the crossover at a longer SID versus a shorter SID. See how the outer edges, small penumbra blurriness? Over here, large penumbra, more blurriness on the edges of it. So at a shorter SID, you have more penumbra, more blurriness than at a longer SID because of the way the beam crosses over and diverges out. So that's why, but we don't have that much of the penumbra to make a difference on a hand X-ray to where we would want to use a longer SID. Plus, we can't get 72 inches on the table, but it's a trade-off. But OID is a big one. So we want the least amount of object to image receptor distance. The smaller the OID, the better the detail or resolution. Closer to the image receptor, sharper image. If we move our hand away, it's going to get bigger and more penumbra. And that is one of the experiments somebody's going to do in the lab. I think the hand group is going to do that one. So more OID is magnifying the image, which is more penumbra. So we have Size and shape is another type of distortion we can have. Size is what we're talking about with magnification. And shape is how the part does not look true to its size anymore. We're changing the shape of it. We do not want to change the size or the shape if we can help it. Sometimes we can't help it. So we want to minimize that for the best quality and the best resolution. So magnification, like we just talked about, is going to happen sometimes, but ways we can reduce magnification is having a longer SID to lower magnification and having a short OID. The way this is worded was confusing. So no object to image receptor distance is the best for magnification, and a longer SID. So this is what we're talking about with magnification. To get the best recorded detail, we do not want to have any OID, and we want to have the longest SID possible. So the worst thing for magnification that you can visibly see, magnification is going to be the easiest thing for you guys to see with your eyes for recorded detail. When we do a magnified image and we compare it to a not magnified image, you can definitely see the loss in recorded detail. So here's what's happening with the source to image receptor distance and how it's projected on to the IR. Same spot, these are representative of the kidneys, but at a shorter SID, it's going to be magnified a little bit more than it would be at a longer SID. So that's why we want long SIDs for less magnification if we're trying to get a better recorded detail. Again, we don't use the long SID on a lot of parts. I don't know why. It should be. It's probably because of that dose thing I was talking about, though, for what we would need to increase to get our beam to get there. And this is another one that's showing you how it's crossing over from this point through and what the outcome is going to be for the size. Depending on how far away the object is, the bigger it's going to get. So object to image receptor distance, magnification down here. So what we're doing here is showing you the difference in the heart size and everything, the chest, how much it takes up on the image receptor, 72 inches and 40 inches. The lungs are almost coming off the board at 40 inches. Heart size, you can see a little bit of magnification of the heart. Detail-wise, I'm thinking here you can see a little bit less fuzziness and blurriness. As you can see, it's kind of fuzzy here. So SID is better resolution at longer SIDs. Ooh, that's a lot to think about, huh? The more SID, the better resolution. OID is object to image receptor distance. So the object being further away from the image receptor is going to make it bigger, closer to the image receptor, more true to size. The more you magnify it, the blurrier it's going to be on the X-ray. Last little part, shape distortion. So we have two types of shape distortion, and that is elongation and foreshortening. And they can happen from not having the central ray lined up right, the part not being lined up, or the image receptor not being all in alignment together. Elongation means that the object is longer than it really is, and this occurs when the tube or the image receptor is not straight and properly aligned. Foreshortening happens when the object becomes shorter than it really is, and this is when the part is not properly aligned. So like a finger up here leaning to the IR, not being straight on a lateral finger. So A, B, and C are all examples to show you what's happening with foreshortening. And D and E is elongation, having the IR angled. And we'll do this in the lab tomorrow too with one of our exposures. So here's what the x-rays look like. This one's longer, this one's shorter, this one's really longer. This picture is from our book, all putting it together, all the different things that could happen on an x-ray. So we have spatial resolution, how well we can see things. We have blurring that could happen. We have artifacts that could happen that we're going to talk about in a minute. We have noise. That's another thing we're going to talk about in a few minutes. All of these things are things that we look at, which are characteristics of our overall visibility of the x-ray and quality of our image. So noise is one thing that can be on an image, and this has a multiple different things in the book that we call noise on an x-ray. One example of noise is fog. So if our image gets fogged with scatter, that is called noise. Other things are motion, blurriness, or underexposure, and we call that specifically, by not having enough photons reaching the IR, quantum noise. So these are kind of definitions of different things that are considered noise on an x-ray.
I have a question. Take like a breather for a minute before we keep going.
Yeah.
My brain is like overloaded.
All right, let me see what time is it.
Yeah,
It's
I
not,
agree.
so let's come back at 10, so 10-minute break. And we are almost done. We're gonna look at a few of these things in the book, and then we will have review if anybody wants to stay on for review after that. But yep, come back in 10 minutes.
Okay.
So the quiz tomorrow is going to be on both of these. PowerPoint. Today just seems like an insane amount of info.
Yes, I'm trying to remember. I printed the quiz. I'm trying to remember what else on it. A little bit of this. Mostly what we were talking about the other day. It's a review.
Okay.
Longer here. Let's try to see if we can get recording going again. But we are going to look at a couple of these in the book. So noise can be fog from the scatter that we see on the x-ray. We have other things that cause noise on the image, motion and quantum noise, which is underexposure, not enough photons making it to the IR. These are the main things that we consider noise. We also have artifacts, and I want to have you guys think about some artifacts that could show up on an x-ray. An artifact is anything that is not wanted on the x-ray.
Like jewelry.
Jewelry, that's the number one. Like necklaces on a chest x-ray, you forget to take off the necklace. Earrings, rings on a hand x-ray. So we need to remove artifacts. Sometimes inpatients have all these wires and EKG leads on them. They're artifacts. If we can move them, we move them. If they absolutely can't be messed with, then we leave them. And they're
They're like
just
hardware, right? Like screws and plates.
patient. Yeah, like a hip replacement, screws, they're artifacts. We can't take them out. They're in the patient, but they're considered artifacts. So good. And the last little section is the math section. So you are going to calculate mass on the next exam, so you will want a calculator. So MA, milliamps, times seconds equals mass. So 100 MA at 1 second, 100 mass. 50 MA at 2 seconds, 100 mass. 200 MA at half a second, still 100 mass. That's the law of reciprocity. Now, I don't know this one. Let me put it in my calculator.
But the gist of it is you're just multiplying the two. That's it.
You're just multiplying 2. There's going to be a tricky one in a minute that I don't have on here. 400 MA at 0.025 seconds, 10 mass. 400 times 0.025 seconds. 1/16 of a second. You need to convert that to seconds. So 1 divided by 6, 0.1666. So you just stop at 1/6, it's fine. So 150 times 0.16, 24 mass. 1/16 of a second, 0.0625. So 250 times 0.0625, 15.6 mass. We can just round it to 15, keep it at 15 mass, it's fine. Now, what if we have milliseconds? We have to convert milliseconds to seconds. So there might be something on a control panel where it's not a whole second. It's a millisecond. So
Isn't that like 0.25 of a second? It's not a whole second.
right, not a whole second, because we usually use fractions of a second. So do my whiteboard. So 0.25 milliseconds is equal to how many seconds? Because we have to convert it to be able to do the math. So for me, I like to just move the decimal. You can also do a mathematical way, which is multiply by 1,000. So if you remember, I don't know, back in math, where you had that little saying, King Hector drinks chocolate milk or something. King Henry died drinking chocolate milk. I think that was the saying my teacher used. Anybody else know what I'm talking about for moving the decimal point? Basically 3 places to get back to seconds. Let me just multiply it by 1,000 and see if I get the same thing, times 0.25, 250. Yep. So we're going to move the decimal point 3 places to get to seconds from milliseconds. So 250 seconds.
A long time.
Why is that not right to me? Because it's not, sorry. 0.25, I need to move the decimal the other way, 0.000 divided by 1,000. Yes. So I'm like, it should be a shorter amount of time. Milliseconds going backwards. So divide by 1,000. So we're going to move the decimal point 3 parts back to the left, 0.00025. So do another one, 0.05. So this, I'm going to do one that's easier. 250 milliseconds is going to be equal to 0.250 seconds. 2.5 milliseconds. We move the decimal back 3 places, 0.025 seconds. Does everybody see what I'm doing with the moving?
Wouldn't it be 0025?
Yeah,
Yeah.
0, 0.
That one, sorry. Move it 3 places back to the left, your decimal point, or you can divide by 1,000 to get it converted to seconds. Because most of the time we are using milliseconds, fractions of a second on our control panel. And ours already has it for you. When you go into the room, you'll see them in the decimal form and the fraction form. So 1/25 of a second, you would divide 1 by 25. Put in my calculator, 1 divided by 25, 0.04 second. So I will have on an exam maybe 1 or 2 of these where you have to calculate mass. Sometimes it'll be a fraction, sometimes it'll be milliseconds, sometimes it'll be seconds, or to find out which value equals that mass.
I have a question.
Uh-huh.
On the PowerPoint, when it said 150 MA at 1/6 of a second, you would just divide 1/6?
Yep. So 1/6 of a second, 1 divided by 6. Yep.
Okay, gotcha. And then you'll times it by the
Whatever the MA, the 150. Yep.
Thank you.
Yep. So that was our ones for you guys to kind of do. So 250 MA times whatever 1 divided by 16 was would give you that mass. So we're going to do this lab tomorrow on elongation, magnification, and foreshortening. And I have this already typed out for us to go into the lab and do. The groups that did not go in the lab for practice yesterday, will go into the lab first for their practice for the comp, for putting a person in a PA projection, a 14 by 17 IRN, and then we'll start our lab. So we'll have lots of time tomorrow to review this, study, and get this down, this geometric and image visibility that we talked about today. And if anybody is wanting to study or do tutoring right now, I am available for about an hour. If you do not want to do it now, if everybody wants to do it later in the day, I would be available probably around 3. So if you're brain dead and don't want to do now. So it's up to you guys. Nobody's wanting to.
I'll stick around today if anybody wants to stick around today.
I'll stick around just because I am brain dead, but I will be available at 3, so we just gotta.
Yeah, can we do it at 3?
Oh no, I can't do 3.
I can't do 3 either.
No, no one can do 3 then? Okay, then we'll do it now then.
All right. So for tutoring, if you want to do it tomorrow, I'll be available after class tomorrow too. Just come with your worksheets from the week. Any questions you have, you can email me ahead of time if you want to, so I'll have that. I do have a couple of people who messaged me some stuff. Pretty much answered them already back though, but I could go over what other people were having issue with. So have a good day. If you're ready to see you tomorrow, if you want to stay on, we can stay on and see. I got the worksheets printed out here for the week. So chapter 5, 7, 8, and 9.
Yeah, we're not doing 10, right? Like the handout says 9 and 10, but we're not doing 10.
Yeah, it's not really chapter 10. It's what we did today. I think the beam restricting device is on there, the 15% rule. So it said chapter 9 and 10 because the book changed. This was the old label for it. So it's really the prime factors and what we talked about today pretty much. If there's anything on there that's not.
That's the one I want to kind of ask. Did I skip over the law of reciprocity?
Yeah, law of reciprocity, yeah. we talked about that being, so if you did 100 MA at 1 second, that's 100 mass. If you did 50 MA at 2 seconds, it's still 100 mass. So law of reciprocity just means you can have multiple mathematical settings that still equal the same mass. Mass is mass. As long as it equals the same mass, that's the law of reciprocity.
So it's the multiple multiple mass settings or equations that equal the same?
Yes.
Okay.
Yep. So the combinations that you can set to give you that same mass.
Can you say it again, Miss Love? I'm sorry. It kind of
Yes.
goes on me.
So if you have like, the easiest is what I've used as an example is never a real one, but 100 MA at 1 second, 100 times 1, that it gives you 100 mass. But what if I changed my MA to 50 and I still wanted 100 mass? I would just have to up my time to 2 seconds. 50 times 2 is 100. So I'd still be able to get 100 mass out of the tube with 2 different combinations of time and MA.
So this is just the equation of how to get masses.
Pretty much.
MAs times the second is mass.
Mhm.
So it's just a written form of the equation.
Yeah, well, it actually is a meaning. Reciprocity meaning you can replicate it over and over again, giving you the same mass every time. So it means that you could have multiple ways to get that same mass. So that's why it's a law. The law of reciprocity just means there's different ways to get the same amount of mass.
Okay.
And we use the shortest exposure time when we can. So if you use a shorter exposure time, you need a higher MA to get the same mass as one with a longer exposure time would be a lower MA. And when you go into the tube, just play with that dial and it'll tell you the mass. So you can go up in MA and you would have to go down in time to get the same mass. And I actually will have you guys set that on the comp day just to make sure you know how to use the settings. I'll tell you a KVP and a mass to do. So we'll start playing with that. Michael's eyes are about it.
I remember you did that. I don't remember exactly because we didn't do it. We just watched you. So I'm sure it'll be easy once we do it. But doing the KVP and then it changed. And so then you had to lower something else.
Yeah, just to make sure that it was giving me the mass I wanted.
And that was just for the warm-ups.
Yeah.
Okay.
And that'll be a good way for you guys to practice messing with the dials too when we go in and do tube warm-ups. All right. Who wants to go first? What you got question-wise?
You know what I really love that you do? I love when you go over these review questions in the back of the book because I feel like it's close to probably what's going to be asked on the test, or like it's helping us
Yeah.
put the concept together.
9. Let's look at chapter 9's back of the book questions. Some of these might not apply. So a quality radiograph must include, and that's on page 111. Quality radiograph, accuracy of the structural lines displayed, yep. Minimal unsharpness, yep. And visibility of the atomic structures. So that one is all of the above. Number 2 in the back of this chapter was visibility factors of a quality radiograph include brightness, spatial resolution, contrast, visibility, what we can see visibly. That is our brightness and contrast. Good. What controls brightness? What controls contrast? That's separate. Those are the controlling factors. So don't get tricked up if it says KVP. KVP controls contrast, but that's not our visibility factor. Contrast is, not KVP. KVP controls contrast that we see on the image. Higher KVPs, longer scale, lower KVPs, shorter scale.
And when you say in contrast, because I'll get confused, that's not the contrast liquid.
Oh, yeah, good question. So yeah, the contrast, when we're talking about it in the visibility part, because we also have subject contrast. Why do we use contrast for so much? I don't know. This is talking about the shades of gray that we see, the differences between the brightness. So brightness is one thing, contrast is the shades. Liquid, oral contrast or injectable contrast is a whole nother contrast, yep.
Okay, so it's the shades of gray.
Mm-hmm.
Okay.
So visibility factors, it would just be the contrast. It wouldn't be the brightness, right?
Both. Brightness and contrast. That's our two visibility.
Oh, because it was oh, okay. For some reason, I thought it was just contrast, but then when I reread it, it made sense that both of them should be it.
Mhm. Yep, if we don't have both of them balanced, we won't be able to see the image right. It'll be messed up. We could have the right amount of exposure, penetration, but we could have too much exposure and it would be too bright. So brightness and contrast together make up our visibility properties. So number 3, which would result in poor quality digital image because of improper processing due to extreme overexposure? Yeah, that's it. So we didn't talk about saturation, but yeah, oversaturated image, yeah.
Oh,
Noise I wanted to show you guys in the book now that everybody's left. We'll have to look at this tomorrow in class. That's the part I wanted to look at in this book. It's on page 107, but I thought there was a picture of it.
because poor quality would mean you saturated it.
Yeah, that was that one that was the picture of the really black and white picture. Maybe we did say saturation in that one, but 108.
What number was that?
4.
Yep, number 3. Number 4 is noise. I want to talk about 108. Page 108 has a picture of noise.
I think my questions are different because I have the older book.
Probably.
Which one's noise?
So B, on picture B of the hip, see in the neck area of the femur, there's like all these little splotches, actually all the way across it. It almost looks like you took an eraser to it and there's little splotches all throughout it. Sometimes I show noise as like a TV that the channel didn't come in all the way, splotches all over it.
Like white noise?
Yeah. So quantum noise means insufficient exposure. The photons didn't hit the IR, so there was no signal, so it doesn't have information for us. So quantum noise is one specific thing for insufficient exposure to the IR. So A, the top hip, good exposure. B, the bottom hip, it's kind of a fuzziness all around it. That's noise on it because there was no information for the detector to give us a picture.
So basically like an eraser mark or something that looks like white noise would be quantum noise.
Yep.
So that's one way to remember it for me.
So quantum noise is specifically talking about exposure to the IR not being enough. And I just got to remember to tell everybody that tomorrow, that picture. But noise, when we just say noise, it's anything that's bad on the X-ray. It could be fog, scatter, it could be quantum noise, and it could be artifacts. Anything that's not wanted on the picture or image.
So noise is basic, because when I'm thinking of noise, I'm thinking of something else, but noise is anything that is basically not wanted or poor. Could it be poor image quality?
Poor image quality, that's what it results in, yep.
Okay, so artifacts, poor image quality.
Motion, blurriness.
Distortion.
Fog, scatter, all of that can be noise, yep.
Okay.
All right. Ooh, I didn't talk about exposure indicator. We got a whole nother chapter for that. We'll skip number 4. If the atomic tissues attenuate the X-ray beam, they are said to have what? Number 5. That's a good one. I'm just going to multiple it down to 2. High subject contrast or low subject contrast?
Low subject contrast.
Attenuate the beam. They're going to absorb the X-ray beam.
Low subject contrast?
So what do you think low subject contrast means? This is talking about the body having the subject matter, what it's made up of, the atomic number.
Would it have high density?
Yeah, kind of. Huh. So let me look to make sure I'm thinking of it right, where it says low subject and high subject contrast.
I'm thinking that it.
Well, I know the low subject contrast, that's That's the person. That depends on the person, right?
That's the body. And Eric, you're right. It means that they attenuate the X-ray beam similarly. High subject contrast means they attenuate it differently. So it's the absorption characteristics. So it comes into play with the density, like you were saying, Jessica, the thickness of the part, the atomic number of the part. So if it has high atomic number, very thick, it's going to absorb more.
It's going to go through it. Right.
So it's the comparing the organs together in it, though, whether it says high or low. So I'm trying to think what that question's really asking. Attenuate the beam equally or low subject contrast. Attenuate the beam in a big difference is high subject contrast. So what you said for that answer is low subject contrast, and that is it. Number 5, if they attenuate about the same equally, they have low subject contrast.
I have a question.
Uh-huh.
Can you explain attenuation, like the definition?
Yeah, that's one of the questions somebody sent me the other day about it. So attenuation is, I think the definition worded somewhat like this, the difference between the primary beam and the exit beam. So they're going to be different. That's what happens through the process of attenuation. So how does attenuation happen? Through photoelectric absorption and through Compton scattering. So those two together is how we get attenuation. So attenuation has absorption in it, but it also has Compton scattering. Absorption, when we talk about it, that's just photoelectric effect being absorbed. Attenuation includes both the scattered photons and the absorbed photons happening in the patient.
If you look at 272, it has the definition for you for attenuation. Reduction in the energy of number of photons in the primary X-ray beam after it interacts with an atomic tissue.
Okay, appreciate it.
So just removing photons from the primary beam, yep.
So if that helps, it's 272 in the glossary.
So on number 6, we can skip that line pairs per millimeter thing, the resolution tool question. Unwanted scatter on the image receptor. Number 7 will likely increase what?
Fog.
The fog. More scatter, more fog. The range of exposure intensities on the image receptor that the image receptor can detect. That's the dynamic range. We don't need that one right now. We're going to go over that in a whole nother chapter. Field of view, we don't need. Pixels, we're not talking about yet. So none of those. And matrix and field of view, no. So that's it for the chapter questions.
And then for differential absorption, isn't that the difference between the primary beam and then the exit beam? Or
yeah, it's how the body absorbs things differently, though. That's talking about the process of attenuation through differential absorption. Everything's going to absorb differently. So differential absorption is more about the atomic makeup, the tissue thickness, the density of the object. So it's more talking about the subject stuff inside.
Could you refresh my mind on chapter 6, quantity and quality?
Uh-huh. So what do you think quality and quantity are? What is quality and what is quantity? First one of them, let's just start with quality. What does quality mean to you when we're talking about the X-ray beam?
Quality.
One or two things that mean quality.
I know the quantity refers to the intensity of number of photons.
Okay.
But I don't know what quality. I mean, quality would, I want to say how the picture looks, but I know that's wrong.
Quality, how the picture looks is something else, but quality and quantity, we're talking about our two main things that we set and we control on the control panel is the quality and the quantity of our beam. So the quantity of our beam is intensity, or the number of photons. And what makes that? What do we pick for our quantity? What do we set? What controlling factor?
Penetration?
No.
No.
For the quantity.
That's quality.
Megan, mass. Mass is our setting that we pick for our quantity. So we heat up the filament for a certain amount of time, it boils off so many electrons. That's how many photons get boiled off. Quality, on the other side, is kVp. That's the potential difference, that's the penetration of our beam. That's the energy of our beam. So quality is our wavelength of our X-ray beam.
The quality is the boiling off of electrons?
No. Mass, heating up the filament, mass is the boiling off of electrons. Quality is the potential difference, the kVp that we put across to how much they slam into it, and that's the energy. So quality is the energy or the penetration of our beam.
Could you say which one's kVp and mass again? I'm sorry.
Yep, quality, kVp. Mass, number of photons.
Wait, did you ask us a question?
Huh?
Did you ask us a question?
All right, let me see, where's number? That was quality and quantity. So what is the difference between the primary and the remnant beam?
Primary, remnant. Primary beam is the one that's, hitting the patients, and remnant is that that's what's behind the patient, that little spot that, I don't know how to say it, but it's like right behind the patient. That's that little section of energy.
Okay. So where's the primary beam come from?
The X-ray tube?
X-ray tube. What exits the tube, that's our primary beam. And then remnant is just what you said, what exits the patient. Are they the same? Hopefully not. Our primary beam has all of our photons in it. Our exit, or our remnant, is what's left over after the interactions happen in the patient.
Why are they not the same? Oh, because
Photoelectric incompetence, difference absorption, attenuation, all of those things is what takes away the primary beam. So factors that affect the quantity of the beam. So things that affect the quantity of the beam. So Megan, you said it earlier. I don't know if you're still here. That's the number of photons. That's the mass. So that's our number one thing. Primary controlling factor of quantity, mass. What else can change the quantity of the beam that reaches the IR?
kVp.
All right. What's going to make more photons reach the IR? Increase or decrease kVp?
Increase kVp.
Yeah, it's more penetrating. More photons are going to make it through. Less are going to be absorbed. We could also say more transmission. How much more? If we increase kVp by 15%, twice as many photons are going to come through because they're that much more penetrating. Another thing that's going to affect the quantity of the beam reaching the IR is the subject contrast, the atomic makeup of the part, what we're X-raying, how much atomic number or tissue thickness there is. A thicker part, more or less quantity reaching the IR with a thicker part?
Miss Love, I'm gonna leave so I can start my flashcards.
Anybody want to type it if you don't want to say it? If you have a thicker part, are you having more X-ray photons reach the IR or less? Thicker part. Less, because more are going to be absorbed. So there could be 2 or 3 different questions with just that one thought. Increase absorption, decrease transmission with the thicker part.
What was the question?
Factors that affect the quantity, and I asked about thickness. A thicker part, what's that going to do with our quantity?
That's gonna increase it, right?
Decrease the quantity reaching the IR because they're going to be absorbed more in a thicker part.
In a thicker part, they're gonna decrease.
That was interactions with matter. So we know differential absorption, transmission, and absorption. So transmission means they made it through, exit the patient. Absorption, they were photoelectrically absorbed in the patient. What's radiolucent, radiopaque?
Oh, I hate that one.
Michael got it, one of them?
Well, radiolucent is it's darker on the image.
Yeah, and why? Because of why? What makes it radiolucent?
The density.
It's easier for X-rays to penetrate it, yeah. It's not as dense. So radiolucent means it's kind of translucent, see-through, X-rays go through it. It's a dark spot on an image. Radiopaque, on the other hand, is more density to it, you could say, more subject matter. It's going to show up on the X-ray. It's going to be an area of white.
And would any questions relate to radiolucent and radiopaque as far as is this high contrast or low contrast? Or?
Not really. I mean, more radiopaque is considered absorbing more, but no, not really like in that matter. What interaction is responsible for absorption on Chapter 8's worksheet?
I know it, but I don't want to answer all.
No, hold on, we'll see.
Hold on, what was the question?
Is it photoelectric effect?
What interaction is responsible for absorption? Good, Janelle.
Yeah, photoelectric effect.
Photoelectric, that's what absorbs the beam. We always say photoelectric absorption to try to tie that in together. What happens from a scattered photon?
Compton effect.
Yep, that scattered photon is low energy. How much lower energy from the incoming photon? Compton loses how much?
1/3.
1/3. So that photon now has about 2/3 of whatever's remainder, and it's going to scatter in a new direction, hitting us. Number one source of occupational exposure is from scatter or fogging the IR. We talked about that thicker part.
Yeah, that thicker part, is it part of the anatomic part?
Yeah. It can be the atomic number, if that's what you're thinking of. Thicker parts and atomic number are 2 different things, but higher atomic number does the same thing that a thicker part does.
So what would be the correct answer for that one?
For a higher atomic number, you tell me. Is it going to absorb more or less of the beam, a higher atomic number?
A higher atomic number will, it will go through it, so it will absorb more.
Yep. Higher atomic number absorbs more photon. Higher Z number, higher atomic number.
So the thicker part of the atomic number, X-rays will be needed to produce a radiographic
2
image.
different things. a thicker part or a higher atomic number. But of course, whatever the atomic number is, that thicker part's going to have it. But a higher they're going to be separate questions. So a thicker part or a higher atomic number are both going to absorb more of the photon or more of the beam. So a thicker arm or shoulder would absorb more photons than a thinner arm. You would need more kVp, more penetration on a thicker arm than you would on a little child's arm.
And doesn't it increase the quality of the X-ray beam and decreases beam attenuation?
So a thicker part increases attenuation, because attenuation is part of that is absorption. So if absorption goes up, so does attenuation. Quality of the beam, we would need a higher quality beam to go through a thicker part because it needs more energy. So the quality of the beam doesn't change. The part thickness doesn't change the beam quality, but we would change our kVp or our penetration depending on the thicker part. So you might get a question about, would you increase or decrease your penetration with a thicker part?
So you would increase it.
Yep. So when you're talking about what the quality of the beam is, easy way to say that, the quality of the beam is the penetrability of the beam or the energy of the beam.
I had a question on the worksheet for number 13. It says, what can the technologist do to change the image brightness?
Okay, we're going to get to that one. Let me see what I said earlier. Megan asked about the thicker and thinner part. So what would you say? I think, Megan, I was talking about the kVp or the penetration. Would you need a more, I think it was more absorption or less absorption with a thicker part or a thinner part? With a thicker part, you'd have more absorption. And then would you need a higher penetration with a thicker part? Yes, more energy with a thicker part. If we increase kVp, we would do that with a thicker part. If it's a thinner part, we would decrease our kVp because it doesn't need as much energy to go through it. I think that's maybe what you're asking, I was saying, hopefully. Number 13, what can the tech do to change the image brightness? So if we want to have more brightness, what's our controlling factor for brightness?
I want to say mass.
Yes. That's the number of photons hitting. That's our exposure to the IR. So we control that with mass. So if we want it to be more bright, more exposed image, and we're opposite. More brightness, a wider spot is more absorption. So that's less exposure to the IR. So would we need less photons or more, or a brighter image?
More photons.
It's tricky. Less, because we want more absorption to happen for brightness. Exposure is hitting the IR, that's darkness. So more exposure is more photons, more brightness is less photons, they're opposite. That's a tricky thought. So to change the brightness of our image, if we want it to be more bright or more white, less photons. If we want it to be darker, more photons. That's more exposure or less bright. Ooh, that was a difficult one.
I have a question.
Number
8 on the, I guess the chapter 8, it's a tissue type that plays the role in image formation. Could you, like, I have a certain, I'm just trying to see the exact answer because it can be like so many things.
Yeah. So tissue type plays a role in image formation due to the fact that there's varying degrees of tissues. What we're talking about with tissue type is bone, fat, muscle, air. So we could put those down there and we could say bone is a higher atomic number, so it's going to absorb more. Air is the lowest. It's going to let everything come through. It's more radiolucent, if we're going back to that term.
I think it's just the phrase image formation that kind of
Yeah.
trips.
So when we have our image, if everybody was made up of the same thing, like the book, we wouldn't see anything. It would all be the same. But because we have different atomic numbers throughout our body, we have bone and air and fat, we can see different shades. So it's the different ways that it absorbs the beam or attenuates the beam, you could say. So the type, depending on its atomic number, is going to absorb differently, so we can see different shades on the X-ray.
So can you answer it by saying just bone, air, and fat?
Yeah, but you want to know more than just that. You want to understand it so you can answer a question about it. You could say,
Bone has more of an atomic number.
So it's going to absorb more. It's going to be on an X-ray. And that's the part of image formation of it, so we can see it because it has a higher atomic number. Do we want to only have a white image if we were all made of calcium and bone or metal? No, we'd look like the Tin Man. We need all those different density tissue makeup to see the image, to have an image formation.
And I figured I would just go through them. Tissue density can be explained by the compactness of atomic particles.
Yep.
Quality of the beam affects its interaction with anatomic tissue.
For number 10?
Yes, ma'am.
What's the quality of the beam? We went over that one. Quality of the beam.
Penetrating.
Good.
Penetration.
More energy.
So quality of the beam is penetrating?
How penetrating or how much energy it is. That's the quality, yep. Higher quality beam, more penetrating. Lower quality, less penetrating or less energy.
And low KVP is better quality, right?
Okay. Lower KVP, I would say, is lower quality. Higher KVP, higher quality beam. But do we want sometimes short scale and sometimes long scale, if that's what you're getting at? Because to me, most people like short scale pictures and they say lower KVP is better, but not necessarily. So don't think of it as that.
I was just thinking more along the lines of lower KVP can be more associated with higher or lower quality.
Yeah, lower KVP, lower quality, lower energy, longer wavelengths. Yeah.
For number 11, what does attenuation do to the overall quality of the beam? I put beam attenuation is decreased with a higher energy X-ray beam and increased with a lower energy X-ray.
Okay, that's true, yeah. So overall quality of the beam, when we attenuate or take out some photons, just like filtration, what does that do to our average energy of the beam?
So it's reducing the energy.
So it takes away photons, but it increases the average energy of the beam. So that was kind of a tricky way of asking that.
So basically beam
overall, it increases our energy of the beam overall, just like dropping the lowest test scores does.
So it decreases and then makes higher energy. And
the overall beam energy is higher, the quality of the beam is higher by attenuation. If you're going to measure out the numbers that exit the patient. The ones that made it out are the high energy ones, so they're going to be overall higher energy now.
So that was the answer.
So you said you're gonna reduce energy, like you're taking some photons away, but also overall gonna be a higher energy.
Yeah, because we're reducing the low energy photons and leaving us with the high ones.
Okay.
The only thing about that is aren't attenuation and transmission indirect?
Yeah.
So like in the sense that you just said, it sounds like they're almost the same. But
So attenuation removes photons from the beam. So we have less photons making it through. So if we have attenuation, what you're saying, transmission, more attenuation, less transmission. So that's why they're indirect. But if we're taking and saying the overall quality of the beam, that's the part of that that makes it that you have to take those energy levels. So instead of 10 photons making it through, only 4 made it through. So now we got to do our average energy out of those 4 instead of the 10. Our average energy went up. So it's a separate concept. I guess that's why it kind of got blurred there. So it's a weird way of asking about the energy level of the beam. The attenuation actually does help our energy level go up of our beam, just like filtration in the tube increases the average energy of the beam. It absorbs some of the photons, gets rid of them.
So for number 12, it says list factors that affect attenuation of the X-ray beam. Wouldn't it be tissue thickness, tissue atomic number, tissue density, and X-ray beam quality?
All those things, yeah.
Would you want us to name all of them, or just name like 1 or 2?
All of them, because you need to know all of them. So if there's a question about any of them, you know how they affect attenuation. So you could even go even further to say a higher atomic number is going to be greater attenuation of the beam. Then you could say a higher density, it's higher attenuation of the beam, just like those questions on our quiz. Yeah, those all affect the beam. For a thicker part, you need a higher quality X-ray beam to penetrate.
And for number 15, the difference between latent image and manifest. Latent is not visible and manifest is visible.
Yep.
We didn't go over that a whole lot, but is that going to be on the exam?
Questions because that's taken off of the registry now. So we won't have that.
Which question?
And we won't have number 16 as well then?
Nope. Or this dynamic image, nope.
Okay, beautiful.
Dynamic we talked about, but we won't have that yet. That's fluoroscopy.
And Janelle, we were talking about layment and manifest. Don't need to worry about that.
Slide and stuff, but I kind of said that's taken off the registry now. They're not going to question you about them because that's more with film.
Okay.
We were calling it that in CR before we processed it. There's an image there, but we can't see it yet. But they're just going to do away with it because it's not even an important factor anymore.
Okay.
Jumping back to chapter 5, can I tell you? Can I ask if this is because I've been having difficulty trying to word the X-ray production. I want to say the MA heats up the filament, electrons are boiled off, the stator rotates the rotor, which spins the anode disc, releasing a positive charge, which attracts the negative charge that bombard the focal spot, thus creating an X-ray beam.
Yep. That's it. X-ray production. Then when they bombard that, 2 types of X-rays are produced. Characteristic and Bremsstrahlung.
Do we have to know that as well?
Yep.
Characteristics and Bremsstrahlung. Okay. And how do you extend the life of a tube? Is it by applying minimum recommended currents, MA and voltage and exposure time that is appropriate to each exam?
Yeah, so there's 4 different things or so that says that we can save the life of our tube. Warming up the tube every morning helps get it ready so it doesn't have the pitting of the anode happening. To use the lowest factors that we can so we don't overheat up the filament too much, and to not rotor a lot. Rotoring is when we halfway hold it down. Right before we get ready to hit expose, it automatically rotors for us. But if we're watching a kid and they start to move, we can let off the rotor. and then we can restart. Each time we're doing that rotoring, we're heating up the filament and boiling off electrons. So if we continue to stop and start, we keep boiling off electrons.
So don't use the rotor as much as well.
Yeah, reducing the use of the rotor, not overheating up the tube to the maximum MA, and warming up our tube every morning to make sure we don't put the anode to mess up our tube. Those are our main three.
I have a question.
Uh-huh.
For this exam coming up, it's going to be everything that we did for week 1, starting with Rinkin. And,
yeah.
Okay, gotcha. All right.
All right, guys. Well, we'll be in class tomorrow, and I'll stay after if anybody wants to. Bring your worksheet if you're working on it. Ask any questions you might have. Think about what you missed on quizzes or exams and see if you understand why you missed them so you don't miss them again, so we can get that straight. Like I told somebody earlier on the break, once it finally clicks, then you'll know it for the rest of the class and hopefully won't get it mixed up. But one little thing being mixed up makes you miss it on all those questions.
Exactly. That's why I was gonna say I'm gonna bring all the worksheets and just go over to make sure that I have it right, that I'm studying it right, because my biggest thing is I'm thinking I get it right, or I think I have it right. Come to find out, it's completely wrong and sideways.
Yeah. When I